My name is Pfluger from the Department of Energy Efficient Buildings. So we do research in energy efficient new buildings, but also refurbishing buildings. And we do research on energy systems, which is in future renewable energy system. And the presentation of today is on long-term decision-making for climate neutrality. Our goal is to have a climate neutral future, and the path to this climate neutrality is a transient one. So the energy system will change over time, and that's the topic of my presentation today. So working today for a carbon-free future of tomorrow. How can we do it, and how can we make decision-making in terms of centuries ahead? So what can help us doing so? Charles Michel, European Council President, said in July 2020 that climate neutrality is no longer a question of choice. It's beyond doubt and necessity. And I say, yeah, that's true, and it's a question of time. And that's all about the presentation of today. How can we decide for the future? First of all, the definition. What does the European Commission mean by climate neutrality? What does this word mean? So does it mean that we don't emit any CO2 anymore? No, it's neutrality means that on one hand, emitting less greenhouse gas, but absorbing more, so that it's a net zero emission that is meant by a climate neutral future. So it's true, we have to reduce the emissions more and more. And as Lindsay told us in the last lecture, energy is one of the biggest parts of emitting CO2 by burning fossil fuels, oil, gas. It's 75% of the European greenhouse gas emissions is based on energy. Let's have a look on the time scale. So since when do we know that greenhouse effect will take place? So it's more the history of science on climate science is longer than 100 years. So Tyndall and Arrhenius knew already a lot about that. Tyndall made research about blocking of infrared radiation by CO2, and Arrhenius calculated the rise of temperature due to CO2 in the atmosphere. And here I post an arrow to sign 2050. That's when European Commission wants to reach climate neutrality. So that's a really, really short period of time ahead of us, and we have to hurry up, and we have to take the right decisions right now. Yeah? And that's difficult because we have a lot of things we cannot foresee, but we have to do the right decisions now on a long-term scale. It's around one generation, and we have to take the right decisions. A closer look to the time scale, the timeline for climate neutrality. This is today, 2024, and in 2030, the European Commission wants to have all member states have the CO2 emissions reduced by 55%. Austria has an ambitious goal. It's climate neutrality in 2040. The European climate neutrality should be reached in 2050. So that's really not a long period of time. Let's have a comparison with our decisions made today. Think about a building. Maybe you want some money and you can buy some building or you want to build a new building, this will have a lifespan of 50 or 100 years or even longer. I myself live in an old building from the 16th century, and it's still good to live in. So it's not limited by 100 years. It can be several hundred years here. But just imagine 100 years. You build it today, and it will exist even longer than 2050. So it will exist in a time where we hope that we reach climate neutrality. So it's after climate neutrality time, so to say so. Yeah, the picture on this slide is of a building which was built in 1991. It's the first passive house in Darmstadt-Kranichstein, and it has a really low energy consumption. And it still has a really low energy consumption. It was heated in the first 10 years or 20 years by gas, and now it's heated by electricity. There's PV on the roof. There is change from gas boiler to heat pump. So the household appliances are really energy saving. It's energy efficient. But the heating system changed over time, but the envelope is still the same. It's energy efficient, it's very well insulated. So it's made a decision in 1991, and it's still the right decision for today. So yeah, just think about what will happen in future after climate neutrality. It still makes sense to have an energy efficient building in those times. So first, another definition. If we emit CO2, it has some certain global warming potential. I think you've heard about this GVP. It's for long-lived greenhouse gas emissions. And then you can calculate in terms of energy how much CO2 is emitted per, for example, megawatt hour energy produced. So this factor is 1 in terms of CO2, but there are also other greenhouse gases like methane or whatever, and they have a different factor. In sometimes it's much higher than 1, and so you multiply it with this factor. But what I also wanted to stress here is the time period of the emissions, how long they stay in the atmosphere. In case of CO2, it's a really long time, more than 100 years time period. Other gases like methane, it's shorter the period remaining, but they may have a higher global warming potential, so they have a higher factor. Example here for methane. You multiply the weight of the methane by the factor. In this case, it's 21. So the CO2 equivalent of methane is, of 1 ton methane, is 21 ton CO2 equivalent. Okay, the time period is shorter, but the effect in terms of global warming is higher. So by definition, the GVP of carbon dioxide is 1. This graph is from a publication where you have in white color the median of the temperature response from emitted greenhouse gas, and you see if you have an emission, we have some certain time delay effect, and then the effect is reduced, but very, very slowly. So it's far more than 100 years in future remaining in the atmosphere. So our decisions now will have an impact of many, many centuries in the futures. Last time we had this film from Andris Nair Magnussen, who wrote the book on time and water. You remember the video we have seen. And he also talked about the time schedule. Over the next 100 years, there will be foundational changes in the nature of water and our Earth. So we have a change in speed, in the speed of changes. Earth Midas forces have forsaken geological time and now change on a human time scale. Yeah? It's one generation, and changes that previously took 100,000 years now happen in 100 years. So yeah, our decisions are really, really important. And we've also seen in this film this waterfall, which has exactly the same amount of volume as the burned oil on a global scale. This is the official numbers from Statista from oil production in 1,000 barrels per day. And this blue line here is 100 million barrels oil per day. So it was rising constantly. Now we have some plateau. That's good to see that it's not always rising. We have some kind of saturation, but it's an impressive big number. Yeah, and with this picture, or you have seen the film, 100 million barrels of oil is the biggest waterfall in Europe, in Iceland, this Dettifoss waterfall, which is the same volume than the oil we burn hour by hour, day by day. Yeah, and this graph I like very much because it's rather precise. The reason why it's so precise is quite easy. The scale, just have a look on the scale. It's minus 3,000 and plus 4,000 years. This is where we live now. And yeah, in the early years of Egypt, Greece, Rome, and so on, there was no fossil fuels in this scale. It's billions tons of sea equivalent per year. But then suddenly, after the Industrial Revolution, we had a peak. This red peak rises and then falls down. Yeah, and that's the truth. It's rather precise. We can't look in the future, but this scale is so big that you can say within the thickness of the line, it's correct. So it's a short rise in energy consumption, CO2 emissions, and then it goes down. Yeah, and then the question is, what's after this time of burning carbon fuel? So we have to rely on renewables. That's the graph of the global fossil CO2 emissions. Yeah, and we have some saturation here. So it's dramatically high, but yeah, it's we have a chance that it's not longer rising, but it will be reduced in future. And the good news, there is no exponential growth. So one question to you, is some students of economics in the room? Somebody? None of them? Okay. Yeah, if I ask economics people, I always get the answer, yeah, we have some exponential growth. But the truth is, it's not exponential, it's linear. And that's a good news, because with linear growth, we can handle somehow. Exponential growth we can't handle. We are sure that's too much. So let's have a look on the GDP, the gross domestic product. There is a presentation. If you want to have a look, it's a video recording you will find under this link from this year. Wolfgang Feist is the founder of Passive House Institute, and also was professor here in Innsbruck. And he gave a lecture about this growth discussion, and it's really interesting. I will show you some of the slides of his presentation, but if you want to hear it in detail, you can have a look on this link and watch the video. It's in English, and yeah. This is a slide of the GDP in Germany relative to 1960, which is 1. You see my my cursor here. In 1960, it's 1, and then we have these dots which are inflation adjusted. So that's the real economic growth with correction by inflation. And do you see any exponential curve? No, it's linear. It's just linear. If you compare it with an exponential line, it would look like this, the red dotted exponential growth, but it's not. Yeah. Let me say it would be horrible if it would look like this, but in fact we have linear growth in a real economic values. Well, somehow there is some faster growth, but then it goes down. So it's some fluctuation year by year, but not long-term exponential growth. And now the good news. So let's have a look on space heating efficiency. That's how we heat our buildings, and how good is the insulation of our buildings, the windows, the building components, and so on. Yeah, we made good progress. On the y-axis, you see here the specific energy for space heating in kilowatt hours per square meter and year. And the trend between 2000 and 2010 was rather linear, and it was downwards. So we had really good savings in the space heating. Then this is a not so good trend. It's stagnation. Nothing changed, and that's politics. So yeah, if from technical point of view, we could have still a decline here in the same inclination. Hopefully we do in future better, resuming the trend from the past years. We could come down in regions which catch up with the renewable potential, which is photovoltaics, wind energy, water, and so on. So we have some limits of efficiency, but we are far off these limits with our buildings today. There's a lot of potential still to reduce our space heat consumption. What was the conclusion of Wolfgang Feist? Yeah, first of all, gross domestic product is growing linearly, not exponential. If the percentage efficiency gain is greater than the percentage growth, it can be compensated. So we have to be faster with efficiency to catch up, or we we keep our or we stop our growth completely. Then we also can catch up easier. If real GDP growth is linear, an improvement in efficiency corresponding to the descending geometric sequence catches up with linear increase. So if you want to watch in detail, just follow the link on Passipedia. It's explained there. Yeah. I just had a look on the global GDP in billion, because the slides you've seen there was from Germany, but it's similar in the worldwide GDP. It's also a linear rise. It's not exponential. And here are the global fossil CO2 emissions. It's also a linear trend. But the rise of the CO2 emissions is not so steep like the rise of the GDP. And that's a good news. So we are gaining efficiency. So efficiency in terms of reduction of CO2 per GDP in $1 billion. So this is the CO2 intensity of global GDP. Yeah, in the first glimpse, it looks also like linear, but that's not correct. If you divide the two values, it's not linear. The curve looks like the red one. If we assume a linear growth of CO2 and a linear GDP extrapolation, then the curve in future looks like the red one. Yeah, and then that's not a good news. If you do business as usual, yeah, that's not enough. Yeah, we don't catch up. So CO2 intensity will not reach zero even after 2100 for business as usual. And we cannot compensate this with CO2 sequestration and other techniques. Yeah, now the question is the GDP the right key performance indicator? There are a lot of key performance indicator, and yeah, for us, for humans, it's not money, it's other performance indicators. Here are some abbreviations which are used in literature. The real energy value added, or the human development index, or the quality of life. So these are all definitions you'll find in scientific papers as yeah, some kind of key performance indicators. So just to explain in detail, what we as humans want is not energy. Nobody of us wants to have energy. We want to have the energy service. What we get out of the energy. How much energy we use for this service, nobody is interested in. We need the service. So we shouldn't list the use the energy as part of the GDP as a key performance indicator. That's misleading. That's not what we want. So, but in many yeah, publications, you find, like here, the Human Development Index, HDI, correlated to energy, and you see, yeah, it's highly correlated, but that's as it is up to now. It's not necessarily correlated directly. If you do something in a more efficient way, it's not correlated. For example, you need a warm room in wintertime. You can insulate your building better, and then you don't lose so much heat through the walls or through the roof, through the windows, and you still have 20 or 21 or 22 degrees centigrade in the room. That's the energy service you have, is a warm room, and you need almost no energy at all. So if you insulate very well, the amount of heat is reduced you need for heating. So there's some decoupling. So many of the publications are research with a rear view mirror. We have to look to the future. How can we proceed in future? How do we have to make our decisions today for a carbon-free future? How about the world population? Again, same picture. It's not exponential. It's it looked somehow like exponential from 1900 up to now. There was some kind of two lines, but since 20 since 1960, it's more or less linear. The population growth is linear. So let's try to calculate the energy consumption per capita, per person. That's interesting in terms of evaluating how efficiently we use our energy. So how much energy does any person on our globe need? This is the world final energy consumption. Yeah, it's rising. There's some kind of plateau here in the last few years, but yeah, on a really, really high level. And this is the final energy per capita, per person on Earth. And there is some kind of saturation phase now. It's not rising so steep anymore. The scale is in pegajoule per person. So yeah, if you extrapolate this, then we would have on the y-axis the total energy consumption, and here the time. This was on a publication. You find the link here. But that's not necessarily like this. We don't need the energy, but the energy services. Let's have on the energy use per person in different countries. You know, perhaps these Our World in Data. It's a really nice page. Please have a look on it. You find really interesting graphs and data there. And I took this map from this Our World in Data homepage. It displays the energy use per person in 2022. The dark red color shows higher kilowatt hours energy use per person, and more orange or yellow one shows the lower one. So in Africa or South America, it's lower, and here the highest energy intensity per person is in Canada, United States, Northern Europe, and Australia. And this map is clickable, so if you have a look on the link, you can just click with the cursor on each country, and you immediately get a graph from the time scale 1965 up to 2022. And let's have a look on Canada. Okay, as we have seen, it's on a really high level, but the trend is negative, so it's reduced. That's a good sign. Well, it's on a high level. It should be much lower, but yeah, what we see, it's the energy per capita per person is reduced over time. We are on the right side of the curve. It's reduced, and this gives hope for the future. Same in Austria. It's reduced. We get better, and one reason is our buildings. Our buildings get better. We are not better in traffic. Unfortunately, we are high spend of energy in traffic, but in buildings, it's much better than the years before. So it's reduced, and also in industry and other sectors, we have good values in energy reduction per person. That's China. Okay, they are rising in energy per person. But on the other hand, they are also rising on renewable energies, so photovoltaics, and be aware that they are a big exporting country. So we consume a lot of products from China. They are produced in China, though these add on the value per person in China. So it should be added in our country because we also consume goods and services from China. This map I like very much. It shows the primary energy per capita in 1999, in gigajoule worldwide, the mean value is this red box. You see here yellow bars for each country, and you see a red box, which is the primary energy mean value in 1999 in gigajoule. If you divide these by the hours of the year at 1,760, then you end up with the power in watt, and this power is 2000 watts. So every person on the earth consumed in this year 1999 a power of 2 kilowatt permanently. So there are countries which are much higher, like United States or or others, and there are countries which consume less, like Africa or South America. You see, it's not uniform over Earth, but the mean value is a power of 2000 watt. And if you think about a power which is more or less sustainable, it's just this value, 2000. If we would freeze the value on this number, it could work sustainable. And that was the reason for the 2000 watt society in Switzerland. You can have a read in internet about these Energieschweiz-Gemeinden, municipalities in Switzerland, have the goal to come down with the per capita consumption of power of 2000 watts. So have all the energy services like residential and traffic and all brought down to 2000 watts. That's the goal. Unfortunately, it's worldwide, it's not like this, it's rising. You see here the 1999 value of 2000, and then it was rising, though all this is not sustainable. We have to reduce it dramatically, but it's possible. The primary energy per capita here in kilowatt hours per year, or in this watt, in this power number, you see the limit value is at 2000, and all countries are above. Ukraine not. Ukraine is below this value. Here a graph of the total final energy consumption in Austria. It was rising more or less like this spread line linearly. It's the number in petajoule, and now it's remaining more or less constant. Okay, we see the GDP is rising, but the total final energy consumption is more or less constant. How about the world per capita energy consumption, PCEC? Yeah, that's the numbers in petajoule. And here I found a graph where both is in one graph, so the energy demand per capita and the real GDP. And again, you see some kind of plateau or even reduction with rising GDP. And that's a good news. We get more and more efficient in terms of energy with our energy services. Okay, we are too slow. It could be more, but it's possible to do so. This slide is from Wolfgang Feist. He gave a lecture in the lecture series of climate protection. You are kindly invited to watch the video. It's recorded on YouTube also. It's about energy services, and I like it very much because it makes so clear that we don't need energy, we need services. That's all. Yeah, And he makes many good examples, like this bottle of coffee. On the left-hand side, you see a coffee pot on a traditional coffee machine with a glass pot and an electric heater below, just to keep the coffee warm. Okay, nobody wants to drink cold coffee. That doesn't taste very well. My coffee is already cold now. But if I do constantly heating, it still would have been hot now. But I could have used an insulated pot or how do you call it, thermos bottle. Yeah? It would be still warm without any heating. So the energy service of hot coffee is to keep it warm, and I don't need any electricity. And you can use these for all and every examples in human life, in industry, in transport, and so on. Just imagine a display, a video display. You have a computer display, it needs some energy. If you have an e-reader with e-ink, it needs almost no energy, only for changing the pages. It needs some electricity, but then you can watch it hours and hours and it doesn't need any electricity. So there are many examples with nearly zero energy and you have some energy service. So on one hand, it's the energy efficiency, and then the other hand, it's the renewables. That's the scenario for Tyrol 2050. So we should come down with the energy consumptions by efficiency by 50%, and the same with a rise of renewables. So, and then we can reach the net zero by this. So we have a chance in both directions, and don't forget the energy efficiency. So efficiency first is the best decision for now. Yeah, how to decide today for a world beyond 2050. It's sure that our energy system is somehow transient, and that's good. That is transient. We shouldn't remain on carbon fuels. We have to change to fully renewable. At the moment, the European Commission says we should track our carbon over time. It's quasi-static LCA. We calculate how much energy we need for production of our building products. Then we calculate how much energy we need for heating the building over time. And then the question of recycling and reuse of the building material. And the period of heating is the most energy consuming one. So efficiency first is the right decision. And then the question is, which KPI should we use? How to decide different scenarios in terms of future decisions? Which KPI to choose? At the moment, we calculate the primary energy PE. That's based on non-renewable, that's on carbon footprint. And in future, we will have total renewable. And I will explain you now about the concept of primary energy renewable. That's a new KPI called PER, primary energy renewable, as a assessment criteria of the future. Yeah, so transient energy system from carbon-driven to fully renewable. Even if we have renewable energy source, at the moment there is still some CO2 emissions inbuilt in the kilowatt hour. It's clear if you have coal or gas or oil, that's CO2 emissions. But for renewables, it's not clear at the very first moment. But you know, also for production of wind power or or for solar or PV facilities, you need some materials and you have to manufacture them and so on. And this graph shows how much CO2 equivalent per kilowatt hour produced energy is built in. So it's at the moment. Yeah? But our energy system will change over time. So in the far future, there is no CO2 emissions anymore because the windmills and the PV plants are built with renewable energy. So in future, we will have nothing else than renewables, and also the manufacturing, the industrial processes are fully CO2 free, though they are there's no inbuilt CO2 equivalent anymore. How we can compare CO2 emissions per kilowatt hour? It's not only the materials, but it's also the complete energy systems. We will have a presentation within this lecture series about grids and grid performance and so on from Technical University of Vienna. And we will hear about base load, peak load, and volatile generation. So in many cases, we need some storage, some short-term storage and long-term storage. In long-term storage, I want to say it's a seasonal storage, and that's really, really expensive. So the short-term may be a battery or a hydropower pump system. But for long-term storage, you need some methane hydro conversion. And then you need some materials for building the materials, the PV panels, and all these things. And at the moment we have, as seen on the last slide, we have some CO2 intensity per kilowatt hour energy produced, but this hopefully will change over time. In future, it will hopefully decrease more and more. So it will decrease in the next few centuries. For example, at the moment, the wind power is at 11 gram per kilowatt hour onshore or 12 offshore. Then you need some fossil backup at the moment, 87 gram per kilowatt onshore, 82 offshore. In hydropower, it's numbers like this, 671. There are tables and databases about that, but they will change over time. They will reduce. And finally, they will end up with zero. But zero doesn't mean that energy doesn't play a role. So even renewables are limited due to economy, due to materials, due to effort for construction. That's for solar power, 48 gram per kilowatt hours. Also need some fossil backup because it's a volatile energy source. You have to have some grid expansion, which is not excluded in these numbers, but also takes some energy. Okay. So for the total electricity mix in Germany, we have a total of 143 grams per kilowatt hour. Yeah, and then we can calculate the next few years. It's some extrapolation somehow, and we call this a so-called dynamic LCA, dynamic forecasting, or if you always take the same numbers, it's a static implementation of LCA. That's what the European Commission asked for at the moment. But in future, we will have technological progress. The energy conversion efficiency rises. As you have heard, we are at numbers of more than 20% for the efficiency of PV electricity consumption now. It's much better than years before. The energy efficiency is higher for our buildings or for our cars or for our industrial processes. the building materials improve, we have better insulation materials and so on, and also the construction and manufacturing improves. We have other dynamic properties like technological process, variation of occupancy behavior. That's the decisions you make at home, at which temperature you want to live in future or whatever. Yeah, we have some other factors which are not constant but dynamic. So, as already mentioned, one of the most powerful levers is the efficiency. So efficiency first. Why is it so important to reduce the energy today if we want to have a total carbon-free future? It's a triple win effect on energy efficiency. First, you save some money. If you don't spend money for energy, you save it. If you save electricity in the building, you also save money, but you also save internal loads. You don't have to cool them out of the building. It's a double effect. So what you don't produce inside the building, you don't have to remove outside of the building. That's less cooling energy. Heating and artificial light reduces consumption in winter, and that's very, very important. Why? We produce a lot of energy in summer by PV, and we need it urgently in winter. So the savings in winter by well-insulated buildings, by reduction of heating, reduces the need of seasonal storages, and that also makes it cheaper. So in a carbon-free future, energy efficiency will reduce resource consumption and environmental impact instead of CO2. So if there is no CO2 emissions, we still have the need to reduce the energy consumption because of the resources and the environmental impact. So now we come to the key performance indicator I already mentioned, which is the primary energy renewable. At the moment, we all calculate with the so-called primary energy. I think you know what primary energy is. Primary energy is the produced energy from fossil, nuclear, or renewable energy. In this factor, in this primary energy factor, only the fossil or nuclear is included. And the primary energy demand is in addition to the actual energy requirements for an energy source, the amount of energy that is required by upstream processes, chains outside the system boundary during the extraction, conversion, distribution of the energy source. Let's have a look. This is the primary energy transformed to secondary and final energy, and we have losses. Losses from transformation, losses from transmission, distribution, and at the very end, we have the useful energy. That's what we use for heating in the building. But before, we have many, many losses. Yeah, and the upstream energy, that's the primary energy. At the moment, it's primary energy non-renewable. And in future, it will all be about renewables, only renewable primary energy. So we need a different kind of factor, a different number, and it's called PER, primary energy renewable. The energy factors in primary energy are not constant, and that's good so. We have more and more renewables in our energy system. So it's reduced from 2010 to today's value, which are lower than 1.5 kilowatt hours primary energy per kilowatt hour. So the factor, the primary energy factor, is reduced, and it will be reduced more and more in future, and hopefully will be around zero in 2050. So primary energy is misleading for long-term assessments. If we decide on values from today for the future, it's not the right decision for one generation ahead because energy is changing. So we build now buildings which will stand even in 100 years or 50 years. So the PE factors are depending on the energy system. The PE factors change over time, and the renewable energy is limited. The resources, the economy, and the space gives the limitations. And renewable energies must be generated, distributed, and if necessary, temporarily stored. That makes it more costly. This means effort, additional energy, infrastructure, and costs. Our buildings have to be designed for a renewable future with a minimum demand. So that's the new definition, the primary energy renewable, PER. The primary energy renewable demand is the end energy multiplied by this factor FPER, the primary energy renewable factor. How is this calculated, or how can we find this value? So first of all, we think about we are already in the future in a fully renewable energy systems in the future. And then energy losses occur primarily when the energy has to be stored temporarily. So for example, PV from summer has to be stored for winter. That's expensive, and that has losses. The amount of losses depends on the temporal correlation between energy demand and the energy supply. So it's more or less half a year if you produce it in summertime and you use it in winter, in November, December, then you have a time shift which is very long and you need seasonal storage. So the PER factor is the amount of renewable energy that must be provided under local conditions to deliver 1 unit of final energy. So you need more energy to produce from renewables to have it as useful energy in wintertime, for example, if it's from solar energy. So the PER factor, depending on final energy source, PV, wind, hydropower. So wind is more or less not constant over the year, but better distributed than PV. Or hydropower. Well, hydropower is also not so good in winter, better in spring, melting ice water and so on. And it depends on the application. So household electricity or heat or whatever you apply the energy for. And it depends on the regional climate. All these PR factors you will find in the PHPP. It's the Passive House Planning package, which is worldwide available. It calculates the energy balance, and it also has all these data stored for the PR factors since 2015, and it's still under progress. It's always renewed and still actual data in it. Wolfgang Feist had the idea in 2040 as a future-oriented sustainability assessment criterion. So it was implemented in this planning package, and the formula is, as you can see here, it's energy supply from renewable sources divided by final energy demand at the building. It's quite a simple definitions, but you have to calculate it according to your energy sources and according to your energy consumption type in the building. This graph is very good to explain how it works. We have energy, renewable energy from different sources, solar, wind, hydropower, and so on. That's our primary electricity renewable from different sources with different time of production. Some of them I can use directly if it fits with our time in consumption and the time of production. I can use it directly, but sometimes it doesn't. Sometimes it has to be stored. So methane storage could be one option to do so, but this storage cycle has some losses. So this arrow for the seasonal storage is smaller than the input, so we lose some energy for storage. This is for the long-term and seasonal storage, and this is for the short-term storage. For daily fluctuations, we have sunlight in during daytime. It's dark in nighttime, so we need some day short-time storage. Yeah, and then that's what we can use for our building. So we need in total more energy input that we get out of it, more renewable, and the relation between is the PER factor. This graph shows the fluctuation of energy production from hydropower, wind power, photovoltaics, and the black line, the load profile. So in wintertime, we have high loads, high energy need, and in summertime, it's lower. That's not a good relation, because in summer we have a high PV production and in wintertime not. Well, the wind power is more or less the same, or even some more in winter, and we have a more or less constant in hydropower, but also more in winter. So we need some storage on a long-term scale, but also on a short-term scale, which you can see here for the electricity supply and demand. This is an overview of some of the PR factors which are stored in the passive house planning package. They depend on the country, so Portugal, India, Germany, Mongolia, whatever, and different for different applications, so domestic electricity, hot water, heating, cooling, humidification, and so on. So heating has a factor of more than 2. Why? Because it has to be stored. It's in wintertime and we have more electricity in summer, so it's a higher value. So cooling is lower because cooling is in summer and we have sunlight. It's even less, so it's directly can be directly used, and we do it by heat pump by a factor from less than 1. That's good. And it differs from different countries, but in principle, it's similar. So we can use it for long-term decision making for buildings. Efficiency measures for heating are given greater weight because they are off seasons when we don't have so much electricity. Cooling is less important in terms of primary energy. Biomass is used only encouraged up to a limited quota because it's limited. We don't have enough biomass for all. Biomass is a good source of heat because we can burn it in winter. It's kind of energy storage, but it's highly limited. So we have to rely on other renewables. Electricity as a heat generator is assumed more positive than previous assessment methods because the future is electric. So all our renewables will be converted to electricity. So wind power, hydropower, PV is all end up in electricity. But we need more of it. We've heard about this net zero, but net zero is cheating. It's not enough to end up with net zero. We need more renewables to have our energy services. This graph shows the wind consumption, which is high because of heating. and the summer consumption, which is lower. And we have a PV production, which is high in summer and low in winter. So this small line here shows the PV need for net zero, but that's not enough because we have to also produce the losses for storage. We need this thicker line to come up with completely renewable. This is the PER PV production we need to also serve for the storage. So the yellow is household electricity, red is hot water, green is heating, and heating is in winter for sure, and cooling in summer. In some countries it's more, then it fits well, but in other it's almost zero. So you can produce your photovoltaics also on the roof, but it's not a good idea to build all bungalow types of buildings because the volume to the surface to volume ratio is bad for a bungalow. You should build multi-family homes. Okay, then the surface on the roof is smaller, but as reference not the roof area is the criterion. So the projected building footprint is the reference. So you can or should use as much as possible for electricity, but the building should have a small footprint and a good surface to volume ratio. So multi-family homes are much better than bungalows. One of these first certified Passive House Plus buildings here in Innsbruck, maybe you know, it's in Pfluger. If you go to west of Innsbruck here, you will find these buildings. These are really passive houses with photovoltaics and solar thermal on the roof. These are Passive House Plus buildings with a PR demand of 48 kilowatt hours per square meter and year, and renewable energy generation of 69 kilowatt hours. This is the rooftop. In the front you see the PV, and in the rear you see the solar thermal. Well, nowadays you would just build PV all on the roof, no more solar thermal, but in those times they also used it for hot water. It also works, it works up to today, but nowadays PV is the matter of choice. Yeah, so the conclusions: climate neutrality is a necessity. Energy is the biggest driver, with 75% in the European greenhouse gas emissions. CO2 remains very long in the atmosphere. We need some long-term decision making for our buildings. They are also long-term decisions, 50 or 100 or more years. The primary energy factor, PER, renewable is the adequate long-term assessment criteria for a climate neutral future. Yeah, that's so far my presentation. Thank you for listening. Okay. Thank you.